Hello students, welcome back, and let us continue our discussion on the stability of a thermodynamic system which is comprised of a non-reactive single phase. So, what we have seen is for an isolated system, the intrinsic stability can be described in terms of its entropy. So, the global stability requires the entropy surface to lie below its family of tangent planes. And so, this is the kind of picture that we have seen for a stable system, where if you change u or v, there will be no spontaneous change in state. Now, this is the kind of condition that is mathematically written for the global stability, and you can also look at the local stability that would require the concavity of entropy locally. So, if I have a concave surface locally, in that case the second derivative of s with respect to the variable like q should be negative. Similarly, del square s del v square should also be negative, and I understand that under the same condition this particular condition should also be satisfied. Now, you can very easily ask me that in an isolated system, maximization of entropy implies minimization of internal energy at equilibrium. So, can I use the concept of internal energy to describe the condition of stability as well? Of course, one can do that. So, what one can do is you will understand that whatever is negative for entropy will become positive for energy. So, the global condition of stability in terms of internal energy will now become u evaluated as at s minus delta s plus u evaluated at s plus delta s minus the 2 times the entropy evaluated at the unperturbed system u v n must be greater than or equal to 0. And therefore, I can also go ahead and say that I can translate these conditions of local stability in terms of entropy to find out the fact that while entropy S should be a concave function of u v n, I can have the condition of local stability in terms of internal energy u, whereby del square u del S square has to be positive. Del square u del v square should also be positive, but this relationship involving the second derivatives, they should remain positive. Now, what I find is that compared to entropy being a concave function of u v n such that its second derivative with respect to its extensive variables u and v are negative, here I am looking at the second derivatives of u with respect to its extensive variables s and v, both are positive. Therefore, my conclusion is internal energy for a system to be stable should be a convex function of its external variables like s and v. Now, moving ahead, therefore, pictorially I can represent it like this. So, I know that the entropy dependence, functional dependence of entropy on its extensive variables should be such that the curve lies below its family of tangent planes. In contrast, what happens in the case of u is that here the functional dependence of u on its natural extensive variables will be such that this curve lies above the family of tangent planes that describe this functional dependence. And as you understand that these behaviors are actually typical of the fact that for as you want to go from here to here, there is always an increase in entropy for the unstable system for a spontaneous process, but if you are trying to go down like this, then the system will not try to undergo the change in state. And because of the presence of a minimum here, therefore, the system will try to be here rather than go anywhere else at the cost of its internal energy. Now, moving ahead, then we can discuss the condition of intrinsic stability for an non-isolated system, because most of the real systems are non-isolated, as we have discussed before. So, what we will do is, we will do an analysis in terms of the thermodynamic potential. So, let us say that I am looking at a thermodynamic potential which is a single variable Legendre transformation of U with respect to P. So, by definition, this energy function, that must be U minus P x. We have seen this before. Here I have, by definition, P must be equal to del U del x, keeping all other conditions constant, and also x must be minus of del E del P. Please note that here I am using this notation C to represent the fact that all other variables in my description of the thermodynamic state are being maintained as constant, as a result of which I am writing partial derivative and not anything else. Now, I am going to use these definitions of the thermodynamic potential E, the variable in the new independent variable P and the old dependent variable x, to find out the condition of intrinsic stability, not in terms of U, but in terms of the thermodynamic potential E. So, how do I do it? The way to do it is as follows. Let us have a look at this definition. P by definition is del U del x. I will take a derivative of P with respect to x. So, del P del x, that must be del square U del x square. So, it is a very simple extrapolation of this. So, now what does it tell me? I know del P del x C is this second derivative. Therefore, I can write down del x del P C, which is the inverse of this derivative, that is equal to inverse of this second derivative. So, by starting from the definition of P, I arrive at this result that del x del P is equal to 1 by del square U del x square. But I can evaluate this partial derivative starting from this expression as well. So, what I find is x is equal to minus del E del P C. Therefore, what is del x del P C? That must be the second derivative of E, the energy function or the thermodynamic potential E. This is the second derivative with respect to P. Now, I compare these two values. When I compare these two expressions, what do I get? I get this very important condition that minus del square E del P square must be equal to inverse of the second derivative of U with respect to x. So, what is the conclusion that you draw from this mathematical expression? I know that U has as its one of its extensive variables the quantity x, and therefore, del square U del x square, it is going to be convex, which means that this is going to be positive. Okay. And therefore, I would say that if U is a convex function of x, then its thermodynamic potential, which is a Legendre transformation of U with respect to P, would be a concave function of P. So, what caused the nature of the function to get reversed? It is the presence of this negative sign over here. So, now this brings us to a quick recapitulation of what we have. If I have an isolated system, I know the thermodynamic potential is U, which is a function of S, V and N. And we have already talked about the condition of stability in terms of this local concave nature of U with respect to its extensive variables, convex nature of U with respect to its extensive variables S and V. Now, when I have a system in contact with a thermostat, I have replaced S by T, and this is a Legendre transformation. So, F is a Legendre transformation of U with respect to S. And now I should find that what would be del square F del T square? That would be the reverse of what the behavior of del square U is with respect to S, and therefore, I say that del square F del T square must be less than or equal to 0. Moving ahead, it is easy to show that del square F del V square is now going to be greater than or equal to 0. I leave this as an assignment to you to show that indeed this is the case. And if I move over and look at the thermodynamic potential where the system is in contact with a thermostat and a barostat, I find that both the conditions give me that they should be less than or equal to 0 as the condition of intrinsic stability locally. Now, from these results, what is it that I have learned? I have learned that starting from these two conditions, I can look at any behavior of F either as a function of T or F as a function of V, and look at the nature of F locally to find out whether it is convex or concave with respect to its variables T and V. Okay. Now, here there is another observation. I see that for all the extensive variables, the thermodynamic potentials are convex with respect to their extensive variables as far as the stability of the system is concerned. But if I am looking at the condition with respect to intensive variables like temperature and pressure, I find that my system must be convex with respect to it. So, in conclusion, we say that for stable closed systems, the thermodynamic potentials are convex functions of extensive variables, but concave functions of intensive variables. So, once again, let us pick up the case of Helmholtz free energy. Here we are looking at the stability of the system by examining the Helmholtz free energy, the behavior of Helmholtz free energy with respect to its intensive variable T. And I find that the system will be stable if F is a concave function of T, as a result of which is a result of the fact that del square F del T square must be less than or equal to 0 for a stable system. But look at this situation where my thermodynamic potential F is being tested against its extensive variable V. So, what is the condition of stability for this system? The condition of stability is that F be a convex function of its extensive variable, and as a result of this I find that del square F del V square is greater than or equal to 0. When you are looking at the Gibbs free energy, I am actually examining only the dependence of G on intensive variables temperature and pressure. Therefore, in these two cases both the second derivatives are going to be less than or equal to 0 for a stable system. Now, we have also seen that how we can altogether do away with the use of these energy functions in a given assessment of a given system. Instead, what we will do is we would try to translate these conditions in terms of response functions. So, what was the relationship that we used to replace the dependence of entropy in terms of measurable quantities? We use the Maxwell's relations. So, if you just sit down and play around with the thermodynamic concepts that we have learned so far, you will be able to show that for a system to be stable, then Cp, that is its specific heat at constant pressure, must be greater than or equal to its specific heat at constant volume, and each of these quantities must be positive. If that is so, then the system will be stable in a single phase. Similarly, you can have the condition of stability in terms of compressibility, and compressibility can be measured either under isothermal condition or under adiabatic conditions. You must know that by definition that compressibility is measured by varying pressure on the system and by noting down the change in volume of the system. This experiment can be done isothermally or adiabatically. If it is carried out isothermally, then the fractional change in volume, fractional decrease in volume with respect to increase in pressure under isothermal condition gives you this isothermal compressibility, and this must be positive for a given stable system. Now, if it so happens that you are looking at the fractional decrease in volume as a result of increasing pressure under adiabatic condition, in that case the compressibility that you measure is the adiabatic compressibility kappa S, and for a stable system kappa T must be greater than or equal to kappa S, and each of these quantities must be greater than or equal to 0. Therefore, as you see that if you are carrying out some experiment and trying to come up with, for example, an equation of state for your given system, in that case if you want to test if for certain values of the state variables, if the system is going to be stable in that particular state, all you need to do is you need to measure the or estimate the response functions like specific heat or compressibility and check if they are positive. And if these relationships as shown here, they are valid, in that case you can very easily say that well, this particular system is going to be stable in a single phase. Now, this brings us to the point where we can actually go ahead and test if we will ever have a phase instability or a phase transition in an ideal gas. So, the next topic that I browse through here is the implications of of whatever we have done here for ideal gases. Now, my starting point would be the fundamental equation for an ideal gas, where I have expressed S as a function of U, V and N. And in a very simple form, this is written as NKB, where the N is the number of gas molecules, Kb is the Boltzmann constant, then logarithm of A, then volume of the gas, then U, which is the internal energy of the gas raised to the power of 3 by 2. Okay. And here you must understand that A is a characteristic constant of the gas, but it is not a dimensionless quantity, because you can only have a dimensionless quantity within a logarithm. Therefore, A is there to cancel out the dimensions of volume and U. Okay. Now, going ahead with this fundamental equation, what I can do is I can try to determine the values of U and V for which the gas is unstable in a single phase. Okay. So, to start with, therefore, I will evaluate del S del U, keeping volume and number constant. Now, if I look at this particular expression, this turns out to be 3 n kb by 2 into U in the denominator. Okay. So, del S del U is a function of U and it does not have any functional dependence on V. So, what is the implication of this result? I can immediately go ahead and find out del square U, del square S del U square, because that is the condition of local stability that I know will give me the an understanding of the stability of the system. This turns out to be minus of 1 by U square with other constant terms. Now, if you look at all these quantities, you immediately conclude that del square S del U square would be less than 0 for all possible values of U, V and N. So, one condition of stability in a single phase is satisfied. Again, since I have del S del U V N is independent of V, it is dependent only on U, then if I take a further second derivative with respect to V, I find that del square S del U del V must be equal to 0. Okay. Now, there is another partial derivative which I need to assess the condition of stability is available to me. Now, what is the other condition that I should be looking at? What is del S del V U N? That is equal to 1 by V. Therefore, I can immediately say that the second derivative of S with respect to V is a negative number. Therefore, I have checked the condition of stability with respect to del square S del V square U N, that is less than 0. And also, since del S del V is 1 by V, it is independent of U. Once again, the second derivative as evaluated like this in the reverse order will be found to be equal to 0. Therefore, I can write down that I have this relationship that both these terms are negative. So, their product must be positive and this quantity is 0. Therefore, the stability condition as expressed by the evaluation of these partial derivatives must give me a positive number. And what does it tell me? If an ideal gas is described by the ideal gas equation and its internal energy is described as 3 n by 2 k T as per the equipartition theorem, then the ideal gas is always stable in a single phase and however much you cool it, it cannot be condensed to a liquid state. This also tells you that phase transition or liquefaction of a gas is a direct consequence of the underlying interaction between different molecules of a gas. Now, let us go ahead and look at the implications of the stability criteria that we looked at for the van der Waals gas, for which I have shown you some of the isotherms plotted as where x axis I have the volume V by V c and on the y axis I have the pressure P by P c. So, if I am at 1, this means that I am at the temperature critical temperature T equal to T c, and this is the volume and the pressure reduced in the units of the relevant critical volume and the pressure respectively. Now, what happens is I am very much higher than the critical temperature, like see 1.5, you see that there is a hyperbolic behavior as predicted by the van der Waals gas, which basically says that the gas is going to behave ideally. Now, as I go on cooling, let us say that if I go on cooling the system at this pressure. So, from higher temperature, if I go to lower and lower temperature, I find that the nature of the isotherm as predicted by the van der Waals gas is going to change. But what I have is now the changed nature has this very interesting feature. So, I am going to show that, as you see from here in this region, you have the variation of pressure like this with respect to the volume. Now, can you quickly identify the region where I am going to have violation of the condition of stability of the system? Without going into details, I can basically show you that if you have these 2 points, and between these 2 points you construct the corresponding Helmholtz free energy, you will find that the Helmholtz free energy is not a stable function between these 2 points as predicted by the van der Waals gas. That immediately says that the system will not be a single gas phase systems between these 2 points, rather it will start dissociating into, it will get converted to a 2 phase system, the liquid and the gas. And this is also indicated by the fact that here locally you have pressure increasing with volume, which indicates that here you have an adiabatic compressibility which is negative. So, that immediately tells you that it is not only a global instability, but also a local instability that you need to take care of. As suggested by Maxwell, he said that you choose these points in such a way that there is an equal area in the negative portion and the positive below and above the straight line, so that the error is cancelled out. And therefore, with this correction, this is how the prediction of an isotherm from a van der Waals gas would look like. So, what do I have here? Instead of this wavy part as indicated by the original van der Waals gas with correction for phase coexistence, now I have a straight line that indicates the liquid gas coexistence, and then this part is the highly incompressible liquid part, and this is the portion of the isotherm corresponding to the compressible portion that corresponds to the single gas phase. So, now you know from today's lecture how to identify regions of stable single phase system for any given experimental situation, and where you expect the system to have 2 stable coexisting phases. So, this is where I will finish my discussion on the stability of thermodynamic systems. Thank you.